So the next thing we're going to do is we've taken this, taken our data, we've plotted our data, we've calculated our percent uncertainties, we've done all that, and I want to take it one step further. You don't, like I said, you don't necessarily have to for this lab, but you get an interesting result. So what we ended up is we ended up getting the slope value, and that slope value is some number. Okay, and it turns out that number times 2. Show up, yep, is equal to the acceleration. Now, the acceleration of an object down the incline is going to be equal to g sine theta, okay? So this is going to be equal to g sine theta. Cool? So this acceleration is equal to 2 times the slope, which is equal to g sine theta. To solve for acceleration, all I have to do is determine what sine theta is. Well, we remember from trigonometry that sine theta is nothing more than opposite over hypotenuse. Okay? Cool? Now, what is my opposite and what is my hypotenuse? Well, when I constructed my incline, when I constructed my experiment, and I'm gonna erase this line right here so we get a little more information. So when I built my incline, here's an exaggerated view of my incline. It's not perfect, mind you. And then I put a block over here. Okay? Put a block on the very end of it. Well, this is theta. That's g sine theta. So the length of my incline, not the measured displacement, but the length of my incline, it turns out to be my hypotenuse. So this is the length of my incline. Okay? So sine theta is opposite over hypotenuse. Well, I've just determined that the hypotenuse is the length. Now, what's my opposite? Well, that turns out to be the height of the block. Okay? So what I end up is, I got the length of this, I've got this, and that's equal to sine theta. So what I can then determine is that g h over L is equal to 2 times my slope. Okay? So get rid of this, and I get g h over L. I can measure h, I can measure L. So with this value, with this numerical value for my slope, I can determine the acceleration due to gravity. I'm slowing gravity down, if you think about it. I'm slowing the acceleration of gravity down. And that's how you measure it. That's how it was measured in Galileo's time. He just simply figured out the way to take an incline and slow down the rate of acceleration. Say, well, if I make it a really shallow incline, then my acceleration is going to be the height divided by the length of my incline is equal to 2 times my slope, or with the g in there. So that's what Galileo did. He slowed down the acceleration due to gravity by introducing this incline. And from there, he was able to determine g by simply measuring the height and simply measuring the length of the incline, and then plotting his data to get a slope for the acceleration. Cool? That's taking it one step further, calculating the acceleration due to gravity. Now, if you're doing it one step further, the results are going to be a little different. So if all you did was do the acceleration down the incline, then you're going to have the estimate and minus the actual divided by the actual, and you're going to get your percent error that way. If you're doing it this way, though, you actually have a literature value. You have a literature value for the acceleration due to gravity. And at the altitude of Denver, g turns out to be 9.80 meters per second squared. Okay? So to calculate your percent difference or your percent discrepancy, the difference, I think it's difference. I'm going to take my measurement for g, what I did this way, and I'm going to subtract it from here. Okay? So whatever I figured out g is from my data, I'm going to take it, and I'm going to subtract it from this value, and then I'm going to divide by this value. And that'll tell me how far I am from the accepted value for the acceleration due to gravity. Cool? That's the falling down the incline.